Some of the no, all of the rules that we learned in the last section for simplifying limits can still work. Even if we have, now we're taking limits as x approaches positive or negative infinity, where in the last section we were just taking limits as x approached some finite value. So take those ideas that you already have. The limit of a sum is the same as the sum of the two limits. The limit of a product is the same as the product of the two limits. And this fact that you just wrote in on page 1, which is that the limit as x approaches infinity of 1 over x is 0. And we can simplify quite a lot of expressions. So there's a place here, there are 2 examples on page 2 in your handout. Here I want to simplify the limit as x approaches infinity of the quantity 5 minus 2 over x squared. So the limit of a subtraction problem, the limit of a difference is the same as the difference of the two limits. So my first step here, to rewrite that limit, so the limit as x approaches infinity of 5 minus the limit as x approaches infinity of 2 over x squared. There's more than one way to think about that, but here where I have the limit as x approaches infinity of 2 over x squared, I can think of that as 2 times 1 over x squared, which is the same as 2 times 1 over x times 1 over x. Now I have all those same, I have a limit of an extended product. I can rewrite that as the product of the limits. And we can see here this fact that you can't read anymore, but that we know is that the limit as x approaches infinity of 1 over x is 0. I can replace all of those limits. The limit as x approaches infinity of the constant 5 is 5. The limit as x approaches infinity of the constant 2 is 2. And then the limit as x approaches infinity of 1 over x is 0. I can replace those values and simplify, and I get the result. That limit is equal to 5. A similar example, again, I have a limit of a product. So I'm going to start by rewriting this as the product of the two limits. So instead of the limit as x approaches infinity of this whole product, 2 over x plus 1 times the quantity 5x squared minus 1 over x squared. I'm going to imagine a multiplication dot right there. So I'm going to think of that as the limit of a product. I'm going to rewrite this as the product of those two limits. So I'm going to have those limits here. And I sort of expand this as I went using those same rules we talked about. The limit of a sum is the same as the sum of the limits. The limit of a product is the same as the product of the two limits. And you can see, so I'll just explain some of these substitutions I made here. So I have the limit as x approaches infinity of 2 over x plus 1 times 5x squared minus 1 over x squared. I'm going to rewrite this as 2 separate limits that I'm going to multiply instead of one limit of a multiplication problem. And then we can start to simplify this in little steps. So here, the limit as x approaches infinity of 1. Well, 1 is a constant function. It's a horizontal line. Doesn't matter which x value you pick along it, your y value is always going to be 1. So the limit as x approaches infinity of 1 is 1. That's how I made that change. Here, the limit as x approaches infinity of 2 times 1 over x. I could rewrite as the limit as x approaches infinity of 2 times the limit as x approaches infinity of 1 over x. The limit as x approaches infinity of 2 is 2, so that's why that part is simplified. You can see here, if I jump down to the next line, what is the limit as x approaches infinity of 1 over x? Well, that's sort of our new fact for this section. That limit is 0, which is why I have that 0 replaced down in here. Okay, so other things to notice, the limit is x approaches infinity of 5x squared over x squared. Notice x squareds will cancel, so that can be simplified, and then I have the limit as x approaches infinity of 5. Again, 5 is a constant, so I'm going to just have that constant value 5 minus the limit as x approaches infinity of 1 over x squared. I could think of as 1 over x times 1 over x, and the limit of 1 over x as x approaches infinity is 0. The limit of 1 over x as x approaches infinity is 0. So this 0 times 0 multiplied together to give me this 0. The answer here is 5, but don't get the idea that the answer to all the questions is 5. We just had 2 in a row by coincidence. So the first big idea in this section is the definition for a horizontal asymptote. When is it that a function has a horizontal asymptote? Second idea in this section, if we want to investigate limits of functions as x approaches positive or negative infinity, one way to do that investigation, it's exactly what we did in the example where we had 2 separate horizontal asymptotes. We want to try to find out which terms dominate the expression. We're going to focus in on those, and they can tell us about the behavior of the function. So I took these next 2 functions from your book, these limit expressions, but I've modified the example slightly. So feel free to just copy it from right here. This is one of the examples we're going to do. I want to find the limit as x approaches infinity of this rational function, 2x to the 5th plus x to the 4th minus x squared plus 1, all divided by 3x squared minus 5x plus 7. So we're going to practice this idea of finding the terms that dominate. So if you think about letting x get bigger and bigger and bigger, which term or terms in that numerator are going to have the most effect on the outcome, on the value of that numerator? And you can see the bigger x gets, the more 2x to the 5th is like pretty much the only part that's going to matter. If x gets to be big enough, 2x to the 5th is going to be so much huger than x to the 4th or x squared or 1 that the rest of those terms are hardly going to contribute to that value of that numerator at all. And similarly, it's the 3x squared term in the denominator that's going to contribute to the value of that denominator the most. So what we can do is, it's a simplifying. So as x gets bigger and bigger, the only parts of this expression that are really going to matter are those 2 terms that we talked about, the 2x to the 5th term in the numerator, the 3x squared term in the denominator. And algebraically, that limit is going to be equal to the limit as x approaches infinity of a new problem where my numerator contains only that dominating numerator term and my denominator contains only that dominating denominator term. So now that I have this expression, the limit as x approaches infinity of 2x to the 5th over 3x squared, I can simplify this using algebra. There's an x squared term that cancels out of the numerator and denominator, and I get here. Now the limit as x approaches infinity of 2x cubed over 3. So what's going to happen to that expression as I let x get bigger and bigger and bigger? Well, notice there's only an x there up in the numerator now. X is going to grow really, really fast as I let x get closer and closer to infinity, and there's nothing about the denominator or any subtractions or anything else anywhere that's going to slow that down. So this limit is actually infinity. You could think about graphing this function. The closest function in your function booklet would be x cubed. And just imagine the x cubed function as x approaches infinity. What happens to the y values? They approach infinity. So this limit approaches infinity. Since infinity isn't actually technically a number, it can't be a limit. So we would say this limit does not exist. We might also say that the limit is infinity. They would get equal credit, but we just have to notice that saying that your limit is infinity is like saying there is no limit, the limit does not exist, because infinity doesn't limit anything. So if we want to think about our original question from the beginning of this section, is there going to be a horizontal asymptote for this function? So my answer here is no. Since there is no one number limit as x approached infinity, there would be no horizontal asymptote for this function. So you could write this one in as our example 7b modified. We're going to find the limit as x goes toward infinity of 2x cubed minus x squared plus x minus 1 divided by the quantity 5x cubed plus x squared plus x minus 5. So same idea, we're going to look for the terms that dominate. Imagine letting x get bigger and bigger and bigger. which term contributes most to that numerator? It's the 2x cubed. And which term contributes most to the denominator? It's here, 5x cubed. So I can rewrite this limit. The limit I was trying to find, that one, is algebraically equivalent to this limit of a much simpler expression. The limit as x approaches infinity of 2x cubed divided by 5x cubed. Well, 2x cubed divided by 5x cubed, I can simplify using algebra very easily. The x cubes cancel, and I have the limit as x approaches infinity of 2/5. Well, y equals 2/5 is a constant function, a horizontal function. It doesn't matter what x value I choose. The output of this function is going to be 2/5, so that limit is equal to 2/5. So in this case, there is a horizontal asymptote for this function at y equals 2/5. And I would expect you to be able to write out a justification. So let's just practice. I would say because the limit as x approached infinity of that function, 2x cubed minus x squared plus x minus 1 over 5x cubed plus x squared plus x minus 5 equals 2/5. So a lot of times in calculus, in this class, and my tests, on the AP test, you're going to be asked to justify your answers. You're going to be able to tie your justification back to some kind of important definition. And this is our definition for when there's a horizontal asymptote. A function, this for example, has a horizontal asymptote at y equals b, y equals some number, if the limit as x approaches infinity of that function is equal to b, that number.